The 8 essential growth pressures are pretty straightforward. This wheel that I've got here on the board or on the screen is one that just tries to put them all out there. When we're talking about removal of things, the term I'm going to use now is substrate removal. To remove anything, that would be the thing that's being acted upon. That's the substrate. The conditions have to be suitable for growth, right? That's what the growth pressures are. The bacteria have to bang into it. In other words, they have to, mixing is an important part of this. We have to get these things intimately connected. So they have to be continuously mixed. And we have to have organisms that have somehow acclimated or become capable, and they're active and present. What we mean by acclimation is that every molecule that is metabolized by a bug, whether it's a BOD or a nitrogen compound or a phosphorus compound or some weird, endocrine disruptor or whatever, the deconstruction of those molecules actually happens with little chemical tools that bacteria make that are specific for that particular step in that reaction. Those little tools are called enzymes, right? So acclimation is an organism encountering a compound or a substrate and somehow in its biochemical machinery figuring out how to code for and express the formation of a protein, assemble a protein that has the right size, shape, and function that actually takes that compound apart. And it's not just one, the enzyme that's functioning, it's not just one. It may have to manufacture 10 to 20 enzymes in a whole sequence to get that whole thing done. In other words, there is a whole lot that's happening when we say, oh yeah, the biology got acclimated. Cool, that's nice. Man, acclimation is the DNA that is inside the cell being translated into information that code, into an RNA that codes for the production of a whole sequence of steps that manufacture the right protein. I mean, it's just miraculous what is going on there. But acclimation is, is easy to say, and it's like, holy cow, that's remarkable that happens. And for that enzyme activation and function to occur, then, guess what? It has to be the right pH. It has to be the right temperature. It has to have the right other components. And so when we talk about the growth pressures, they really are fundamentally what is holding up the ability of that biology to meet the challenge, to adapt to the circumstances that we provided to it. And this is how some of the plastics that have been disposed in the ocean that have a finite half-life, that have a 1,000-year half-life, that are non-degradable. Nothing will touch it. And it turns out, there's a bacterium that can now manufacture the enzyme that will actually break that thing down. Holy cow, isn't that cool? So there's tremendous power in kind of these very simple bullet points. So the enzymes that are catalyzing all of these reactions are obviously one of the end games that we manage the growth pressures around. Of the 8 growth pressures that we had on that wheel there, probably the one that ends up being the most, kind of the biggest ongoing trigger is actually the food load, the BOD load. Now, F to M is if you have been in the activated sludge world very long, you've heard about F to M. If you're new to it, you will. F to M is a concept of trying to understand what the F is, that's the amount of food that's available, and have some balance then that is adjusted for that F, that's the microbial fraction, right? And so F to M is a relationship then between available substrate to be utilized, F, and the amount of biomass that's going to eat that F, M. And so it makes perfect sense, that there is some reasonable F to M, because that is going to drive the microbial growth. Growth rate, then, is a function of the F to M. Because the F is what's delivering the energy, right, for the microbe to do the M replication part. So it makes perfect sense. What is the problem, though, with F to M as a control technique? Or is there a problem with it? Thank you. You can't control the F, and you have limited control over the M. So while it's a hugely important, the bugs really give a rip about it, and we can't do a whole lot about it in the short term, right? And so and frankly, it's a hard thing to measure, because how do you measure the F? Well, we have to do a lab test of some sort. And so what do you measure F with? The BOD. Okay. Well, I think it's obvious there that the BOD test is going to, we'll know what that is in 6 days probably, because it takes 5 days to run the test and we get the data back. So obviously we're using a value that is historical, but we've got CODs, and so we have workarounds to try to get some measurement of F. But it's difficult to measure that F part. How do you measure the M part? Yeah, exactly. Mix liquor bottles. That's how we all do it. It's the best we can do to get the M. But what matters is the F to the viable M. It's the M that's really going to eat the F that we have a hard time with, right? So we can, we can kind of get the MLVSS, and it's an estimation of the bug fraction, but we don't know what part of that's viable or not, right? So they all have their Achilles heels, but it's very hard to pick up a manual or look at a design document and not have an F to M target in there. And so it's something that we want to fully understand and appreciate. F is driving the growth of M, right? And so the control then, if we can't control F, can you control M? And how do you control M then? You control M through wasting, right? And so really, I think what F to M is trying to get at is, how do we waste properly? Because to waste or not to waste, that is the question, right? The plague of mankind. To waste or not. If we can get wasting right, we are real close to the goal line. That is the tail that wags the dog, is wasting. So F to M is a maneuver to try to get to know what to do with the M piece. Right? So if the goal is to get a way to waste, then are there other means of getting a wasting rate than trying to target an F to M? And I would submit that there are. And I think that use of a sludge age or an SRT goal for wasting beats the targeting of an F to M every time out of the gate in my book. Now, ultimately, they're going to try to get you to the same place, but I would say, as you're trying to reach a wasting decision, hitting an F to M target is very problematic for the reasons that we cited. But we've got to have the most reliable wasting strategy that we can to get that F to M actually correct, and an SRT type of control, I think, makes a lot of sense. Dissolved oxygen, probably comes right in there second. You know, what's really going to drive that culture? And how much food does it have? And do we have the oxygen to burn it up? This is kind of like running an engine. You know, you put fuel fuel through the engine. You better have the oxygen to supply it, right? So if you've got a, let's take a, let's see, you don't have snowmobiles in Texas. Internal combustion, in a lawnmower, you know, got a gas lawnmower. You fire it up and it's running the way it's supposed to run. Burning fuel, it's consuming oxygen, carburetor's working fine. Now let's start pulling the choke on that engine. What happens when we start to choke the engine and pull the choke?
Starts sputtering.
Starts sputtering. Why? The fuel to air ratio is off. Okay. What's happening to the power output of that thing when it's choked? It's going down. And are you completely combusting the fuel or not that's going through it? No. So what's happening with the exhaust pipe? With the exhaust?
It's getting low down fuel.
It's getting low down the fuel. So I've got unburned fuel coming out the exhaust pipe. Okay. So if we can think of your activated slug system as a little engine, we cannot run oxygen, we can't choke it, because the exhaust pipe of our plant is your outfall. And if we're running oxygen starved, then the fuel that's going to get out is not gasoline. What's the test that measures the fuel? The BOD, yeah. We're going to see the carbon, dirty exhaust. Just makes sense, right? So if we're trying to really get complete combustion of the fuel, then that little microbiological engine cannot run oxygen starved. Probably no new discovery there, but we want to be thinking about that way. So the whole idea of energy conversion is something that we're really kind of making a big deal out of, because that's what the bug cares about. We use the BOD test then as our measurement of energy for the system. If you went, we got denitrification, that's cool. So if we go to the grocery store and we're looking at nutritional labels now, of course this is probably, it's not going to have one because it's just water, but anything you pick up in the grocery store now by law has got a nutritional label, right? And the top line, when you look at that thing, is going to tell you how much energy is in that thing. What do we call that? Calories, exactly. It's going to state how many calories. And if you pick up, you pick up a sample of wastewater and you look at that, the BOD value is the calories. Okay, so we call it calories when we're eating it. We call it BOD when the bugs are eating it. It's the same thing. It's the amount of energy that's released when the cell combusts. Okay. So oxygen, big deal. Third, growth pressure, hydraulic retention time. Right? How much time does it have to do its thing? Remember that sludge that I showed you that was just anemic. It didn't have any enough biopolymer. It burned everything out, and we were trying to figure out how do we put some meat on the guy's bones. It's got too much retention time. You can have too much too little, right? So the hydraulic retention time of the system is a growth pressure. It's going to dictate what kind of organisms can survive in the niche. Turns out that if we want to change the community composition of the biology, it's like, I need to have some bugs that can chew on this thing that they can't, that I've got to get removed. How do I change the community composition? Well, I have to change the growth rate of the system. I either have to make it grow faster or slower, but I have to make it advantageous to the organism that is, I want to have populate there. The bacteria, we had like 300 different species of bacteria in that example that we were using this morning from cruise. Every one that's there had a growth rate that was faster than the washout rate of the system. Otherwise, it couldn't have been, this number's up to be recognized, right? So there's a growth rate, that's the rate that it takes for a microbe to replicate and get more of itself. And there's a washout rate, which is a normal die-off and a removal from the system through loss over the effluent weir or over to solids handling, right? So there's always this uncertainty in the microbial world about who gets to stay. Well, you darn well better be able to keep up, grow as faster than we're removing you, or your numbers will deplete and your share of the pie is going to be taken over by something else that is going to eat that particular part of the lunch. So we change community composition by wasting rate. Bugs grow at a different rate. It's like it's the reason why if you got like a strep throat, Streptococcus pyogenes, it's a very fast-growing bacterium. Makes you real sick. Get strep throat, take an antibiotic, and within 24 hours, then you're getting better. Because strep grows really fast, and the antibiotic interrupts the growth of that thing at the cell division cycle, right? And so you're taking advantage, you understand the growth rate of that organism and how to attack it. If you take something like tuberculosis, Mycobacterium TB, that organism divides really, really slowly. One cell division may take days, whereas strep pyogenes, minutes. You get tuberculosis, you're in for a long haul because you're having to stop that thing at cell division, right? And so there's these differences in growth rates play out. It's not that we're trying to go to medical school here. What we're trying to do is understand that the same principles that are being taught to doctors apply to us as wastewater professionals, because we're understanding microbial ecology and growth rates and making moves to create the culture that is healthy for us. So wasting rate is a big deal in selecting them for the right species. And we'll be covering nitrification and phosphorus removal as separate items tomorrow. But one of the things that you're going to see is that nitrifiers, the bacteria that like to oxidize ammonia and get their energy, are pretty slow growers. And so we have to have a wasting rate that accommodates that. The phosphorus removing bugs, those are heterotrophs that divide very fast, and they can keep up. So when we're optimizing DNR, we always have to default to the nitrification biology because it has a lower or slower cell generation time. Right? It also has a different temperature tolerance, so that growth pressure of temperature plays in there. So these things are kind of subtle, but I don't like to just kind of throw 8 growth pressures on the wall and say those are them and move on. That's the nuances of them that is where the curiosity that will lead to the discoveries in the next decade or two are going to come from. So that's my reason for putting effort into this. Okay. The amount and health of the biomass. So this is, the amount of the biomass is the other half of the FDM equation. That's the M part. I put the health of the biomass in there too because we see systems that have I'll give you a case in point. This was a treatment plant I was working with in Alberta, Canada, and it had a very high mixed liquor concentration. And in fact, do you remember that clarifier where the blanket was overflowing, where it was bulking? It was this horrible 2,000 milligram per liter effluent. That was this plant. They had a high mixed liquor, 7,000 milligrams per liter, high mixed liquor, and the solids flux in the clarifier, it could not tolerate it as an SPI. Blah, 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 blah. So I said to my good friend who's running this plant, we've got to get the mixed liquor down. We've got to waste. I can't do that. Why? Well, because I need that amount of mixed liquor to meet my FDM target. In other words, he was locked into, and almost by fear of physical punishment, to hit that F to M target. And the mixed liquor was being held at that level. He had F to M calculated to 4 decimal places. I mean, he was hit, but you could see what was happening in the clarifier, right? So, I mean, Lennon is a smart guy. He wasn't, I'm not saying, he spent all day climbing up Mount Stupid. He's a good guy, but the F to M commitment that they had made was so firm that it led to the problems that you saw. So I was like, Lennon, we've got to get that mixed liquor down. No, we can't do that because of the FDM. Okay. We did a viable assessment of that mixed liquor. And it had a horribly low viable fraction. I mean, it's like, it was under 10% of that 7,000 milligram per liter mixed liquor was active fraction. Like, holy cow, it's dead weight, right? So I said, look, for no other reason than to prevent the overflow of the beds, we've got to get the mixed liquor down. We're dropping the mixed liquor. We've got to get it under 5,000. That's where we got to go. I will go to jail with you if you have to go to jail, but we got to go there. So we dropped the mixed liquor. And I said, and by the way, in all likelihood, what you're going to see is, and I'm not a genius, I'm just applying basic common sense that everyone here, I'm sure, is going to get, is that we get rid of the dead weight, it's going to grow new stuff to take its place. And there are only a certain number of live cells that he had food to feed. And so the viable part's going to come up when we get the dead stuff out of there. And if we could actually calculate the F to M based on the viable fraction, you see that we actually are hitting the F to M. But we can't measure viable fractions easily. So it's just a theory. So you can make it a reality. But in fact, yes, we dropped the mixed liquor, and the viable fraction blew up. I mean, it came. It was remarkable. And the story went from fairy tale to truth. Right? And so within that construct that we sometimes find ourselves, where we're holding to a belief around the numbers, think just one level deeper below those numbers and think, what if what I just described actually is true? And I promise you that it is in this case. So the F to M part, F to M, the M keeps adjusting its viable fraction. That's the insidious part of this. The M keeps adjusting its viable fraction as conditions change. And there's only a certain number of mouths that you can feed. Now, I'm not saying that you can be completely oblivious to the sludge age target, because we do have to accommodate the growth rate of the slowest growers that we have to depend upon. But when you think of F to M, think about it as a little bit more of a complicated equation than simply give me the BOD number and give me the mixed liquor ball over number, and I'm going to divide the two and tell you what that is. Because the MLVSS number, you could have a highly variable value, and as it turns out, in Lyndon's case, it was significant. Nutrients are come into the growth picture window By nutrients, we're talking here about nitrogen and phosphorus. And there will be carbon to nitrogen ratios and carbon to phosphorus ratios that we are going to try to hit. Now, there are more nutrients that are involved in cellular growth than just the carbon and nitrogen and phosphorus that we're focusing the course on. But the other trace nutrients are typically not relevant for most municipal systems. If we're dealing with industrial waste that have highly purified water sources to begin with, where most ions have been removed to begin with, ultra-filtered water, ultra-pure, we may have to be supplementing or adding other things. The carbon, nitrogen, and phosphorus are big. Of course, temperature then is number 6 on the list. pH and alkalinity, then 7, and we'll get back to these. And then the 8th one is what I call the negative growth pressure, but it can be big. I think I've illustrated already or mentioned kind of anecdotally examples of inhibitory compounds that are significant growth pressures. And in fact, here at Cruise, we had that tetramethyl ammonium hydroxide case study that was the 2018-2019 event that illustrates exactly this effect. So when we're looking at our system, that's kind of the what the bug is digesting all time, real time, rinse and repeat over and over and over again. They are all playing synergistically, antagonistically with each other. They never occur in isolation. They're always occurring overlapping. So getting a plant stabilized, I look at it as its 8 growth pressures are kind of like legs on a stool, and it's an 8-legged stool. One leg gets a little short. The stool's not very wobbly, but when we knock 2 or 3 of the legs out of kilter, then the plant starts to destabilize. And I would submit that most often plants fail by what I call the sum of the stresses. In other words, it's very hard to bring a plant down with one, but the sum of things typically cause that. So organic looting, we'll take these. I kind of said my piece about the BOD and the COD. Its relative biodegradability is a factor, particularly when it comes to the phosphorus removal biology. We'll cover that tomorrow. And I've said my piece about F2M and the challenges around measuring the food, the microorganisms, and the way the system actually tries to keep adjusting the viable or active part of the microorganism fraction to accommodate. Wasting is the tail that wags the dog. Wasting controls the FDI. It controls the rate that the biology is growing, and it creates the composition of the community. So if there was one piece that we have to get as right as we can get it, it is wasting. And when the EPA invested billions of dollars back in to implement the Clean Water Act with publicly owned building of publicly owned treatment works, more than half of the plants that were initially built with public funding failed to meet their discharge limits, failed to meet their design outcomes. The Congress commissioned a study that tried to determine what went wrong, okay? And out of that, they developed a program called a CPE, a Comprehensive Performance Evaluation. It's a protocol to go in and look at facilities that are underperforming and to find out what things are wrong. And it turns out that there was never a single thing. There was actually hundreds of things that were the teams that were doing this evaluation were finding were contributing to underperforming plants. And there's a point to my story here. There were things that continued to reoccur over and over and over again as contributing to plants that didn't meet the requirements of the design investment. And number 5, on the top, so I think there was 267 different things that they found, but there was a top 10 list. And in the top 10, the number 5 cause of the, maybe it was 267 plants they evaluated. There's hundreds of plants that were evaluated. The number 5 cause was inadequate sludge handling. These were all new plants that were built and didn't measure up. Comes out in inadequate sludge handling. And that's why this wasting piece ends up really being the deal. If we can't waste when we need to waste and have that stay put where we put it, there's your sign. Okay? There is your sign. Solve that one and a whole lot of other problems go away. You know, it's interesting. The number 1 cause, number 2 cause, and the number 3 causes of underperforming plants, guess what they were?
Laziness.
No, not laziness. But they were all people problems.
Close enough.
The first one was a lack of understanding of biological treatment. Universal across all the plants. It wasn't because the people were stupid. These are smart people. But none of us are born knowing this stuff, right? Number 2, inadequate process control testing and understanding and interpretation of data. So these are things that you guys have known forever, and you've been working on this for my whole career. So I'm not telling you anything you don't know, but I'm certainly saying that the work that we do here together is certainly borne out in the history of how wastewater has moved forward, stumbling at times as we go. And lessons learned is that we have to learn this kind of the hard way, right? All right. So the idea here is that I've been throwing out here to consider is FDM. I'm a big fan if we can get the F to M that's the viable part of the M. Try to kind of accommodate that part. COD versus BOD. We had already discussion on this, so this is a repeat slide. That we're trying to do those measurements. We know that it varies. We're gonna. I don't think there's more to say about the changes. I think I made my point on this one going in. So on the carbon load, I think we've got that one out of the way. So DO control. Let's move off of the food. Even though I said that's the first and most important. Let's leave food behind. Go to DO. What do we got going on here? Oh. This is DO control now. Believe me, this is DO control.
The average going 6 yearly.
You got it. Right, yeah. Is it? Yeah. You think your day span? Let's adjust. Let's fix the DO problem in the aeration basin. Okay, so who's going in today? Let's suit up. These guys. These are hard hat. I mean, they're not going in open face. This is a hard hat. They were in 3 days a week for months to try to keep DO in the system. So yeah, it can, DO control, easy to say. You guys perfected like the maestros that you are. It could get ugly, dirty. Yeah. So a lot of money around DO. Some terminology just for educational purposes. Terminology, we use the term aerobic or aerobe. It's an organism that uses free molecular oxygen. We are aerobes. We use the term anaerobic. It uses a oxygen is in a combined form. It's not free molecular oxygen. Facultative are bacteria that can go either way. Well, we can't survive without oxygen. We cannot survive without oxygen. So we are obligated to be aerobes. Most of the bacteria that live in the activated sludge system are facultative. That means that they can utilize oxygen bacteria in the culture can utilize oxygen, or when the oxygen is no longer there, they simply switch to a different metabolic pathway where they continue to oxidize compounds, but do so through a different metabolic pathway. So they got dual gears. That's very cool. But think about it. If you're an activated sludge bug, you spend part of your time in the aeration basin where you're an aerobe. And where do you go from the aeration basin? Final clarifier. What's the oxygen concentration in the final clarifier bed? Lower now. And then from there, you come back and cruise. And decruise, where do you go? To the anaerobic, which is no oxygen. And then from there, you're going back anoxic and then anaerobic. So you're going through very different pressure points from an oxidation reduction potential standpoint. So doesn't it make sense that the biology that is selected for are the organisms that can do it, that can tolerate all of those? Now, they may not perform some functions under an anaerobic condition, but they certainly are facultative and can make it through. So we are dealing primarily with facultative biology in the activated sludge world. You've seen this graphic now. The anaerobic part, they're in the front end of the reactor, or front end of the basin, followed by an anoxic, followed by an oxic, and then it becomes anoxic again. So if we put those terms applied to your plant, that's how they would lay out. Now, this is what's called the electron tower, and it's really a way of expressing the energy that's yielded to the biology, depending on what they use as the final electron acceptor in their metabolic electron transport chain. So oxygen sits at the highest point. If you can oxidize something with oxygen, it delivers the most energy, so that is the most desirable thing to do. Bugs will do what rewards them most. When oxygen is no longer available, the next energy yielding molecule is nitrate, and that's what we call anoxic. That would be the selector in the bioreactor. And then we move on down and we go to sulfate, and then iron, carbonate, and hydrogen. So as you go, so remember, these are compounds are being reduced. Oxygen, when it's reduced by the bacteria, gets reduced to water. Nitrate gets reduced to nitrogen gas. That's exactly what it did here in the vessel, in the beaker, right? Nitrogen gas floated the sludge up. Sulfate, when they finally get the nitrate gone, they're going to switch to sulfate. They're going to reduce that and make H2S, hydrogen sulfide. We've all smelled that one. And then carbonates get reduced to methane, right? So as a sludge goes from aerobic to anoxic, it floats, then it stinks, and then it blows up. All right, metabolic switching. So it's all it's all based on energy yield to the cell. They'll do what gives them the best outcome. Your DO system has a couple of purposes. One is to provide the oxygen for respiration, and the metabolic work that's going to be done. That's both carbon and nitrogen removal for phosphorus uptake and for respiration, but it's also the mixing device. Typically, we're relying on our aeration system to also be our tank mixer. Here at Cruise, we've got then aeration control. That's ammonia-based aeration control. And I'm not sure if these targets are still exactly right, but correct me if I'm getting this wrong. That's looking
A little hard.
A little high, actually.
these are a little high now?
0.5 to 1 and B. 1.25 to 1.75 and C.
Good. So you've dialed that back. That's excellent. And I will correct this graphic so that it reflects the new condition. And my apologies for not updating that to be current. But as it turns out, Comamox, this complete ammonia oxidizer, is an organism that tolerates or can be selected for by lower DO set points. And we like the idea of having a complete ammonia oxidizer and be able to put less air in to get that, because that's code for a significant amount of money. So we can do the job with a bug that can get by with lower oxygen levels. This is a graphic that's trying to illustrate the idea that if we look at a flock, there's a dissolved oxygen, and we look at the DO that would be measured, it's going to be lower inside the flock, in the center of the flock, than it would be on the outside, right? And so there's what's called a diffusion gradient from the outside to the inside. And this was hypothesized decades ago out of David Jenkins' shop at Berkeley to propose the means by which certain filaments had a tendency to cause bulking because of low DO, what they called low DO filaments. Styrolus natans being one of those, type 1701 being another. And the idea was that the filament, because it's oriented out towards the bulk solution, enjoyed higher DOs, and because of the DO decline as you work into the flock, that it would be a selective pressure for filaments. So out of that then came a school of thought that said, oh yeah, there's some low DO filaments that we can control with DO. That story was way overtold and overpromised, partially true, but largely kind of old news. But the Styrolus natans, and that's an organism that we've had here in Texas, of course, type 1701, and H. hydrosis. Those are the three that have normally been called your low DO filaments. What I'm trying to illustrate in this graphic then is the fact that now you're growing these large granules, right? And these granules then have the same gradient of oxygen availability from the outside, where you measure it with your DO probe, through the flock as those molecules try to make their way through. Ammonia oxidation, this is what nitrifiers are doing, right? Ammonium is being oxidized to nitrite, to nitrate. And once it's here in an anoxic, no oxygen part of the flock, that nitrate then can be denitrified. You get that simultaneous nitrification and denitrification because of the dynamics of the flock. Okay. Also going along for the ride is we've got DOD also being oxidized simultaneously to carbon dioxide and water. So we're kind of showing the whole kit and caboodle of nitrification, denitrification, carbonaceous oxidation, all on one graphic to say, yeah, this stuff is going on simultaneously. Nutrients are typically taken up proportionate to the BOD load. The textbooks will tell you 100 to 5 to 1, carbon, nitrogen, phosphorus ratio is the typical stoichiometric relationship. That's a starting spot. It's not the ending spot. If we look at a single bacterial cell on a dry weight basis, it's about 50% carbon, about 1% phosphorus, about 10% nitrogen. If you tracked 100 parts of carbon, and that carbon was assimilated by the cell, and the cell becomes 50% carbon, the other 50% goes off as CO2. So half of the carbon leaves the system through byproducts of respiration. The other half goes into cell growth. And if 10% of that cell that grew is supposed to be nitrogen, then it's 10% of the 50 that was utilized is where the 100 to 5 comes from. So these ratios that you will see in the textbooks are based on that theory of a certain conversion, or what we call cell yield. All right. So you're going to get some phosphorus taken up, some nitrogen taken up, simply by the fact that you're building bugs that have all of those atoms in their structure. And these, you can, I just pulled out some data from the data that you typically have been getting it from the advanced analytical work that shows, yeah, that you're measuring the biomass nitrogen and phosphorus concentration, so you keep track of those. So these are things that people measure. The problem, of course, with nitrogen in the effluent is that it can cause toxicity to fish. And we're certainly familiar with the fact that nitrification and the resultant denitrification may cause some effluent turbidity if it depopulates. We've also experienced here at Cruise the dropping of pH and alkalinity, because nitrification is a big alkalinity consumer. I'll cover that in the morning when we take on nitrification. But the nitrogen challenges are can be onerous. Denitrification, the chlorophyll, we showed you the floating sludges. There's an oxygen demand to nitrification that is something to be reckoned with. And there may be certainly the power costs and the chemical feeds if we have to supplement alkalinity. And finally, partial nitrification causes chlorine demand because of nitrite lock, which we've already kind of talked about. So nitrogen is a formidable component that can bite us a number of ways. The temperature is something that is kind of a biological accelerator pedal. The warmer the temperature gets, the faster biological growth happens. The books will say somewhere between 35 and 50% increase in metabolic rate for every 10 degrees rise Celsius. Rule of thumb, it's not carved in stone, but the idea is the warmer it gets, the faster the metabolic rate. Nitrifiers are slow growers, and so we adjust the sludge age or the cell residence time depending on what the temperature is. You'll see this more tomorrow. Okay. But temperature affects the growth rate, and all of the other organisms that are in there. Actually, temperature can get so hot that you'll lose all the higher life forms. We don't see this often in municipal systems. I see it a lot in industrial systems that are operating at higher temperatures than you know. It's not uncommon to have an activated sludge system running at well over 100 degrees Fahrenheit, 105, 108. I've got one right now that's pushing 109. These are industrial plants. And they have a very hard time growing any higher life forms, but they do a real good job of BOD removal. So life is good, and you don't see any of our friends that like to wave and greet the crowd. So there you have it. But nitrification is temperature sensitive, so we will account for that tomorrow. I covered this about the increase in temperature with a resultant change in growth rate. So this is just illustrating cooling. This is also an industrial situation. I don't believe too many municipal plants do have cooling towers or other means to adjust temperature. Move on from that. pH, of course, it's a logarithmic scale, right? pH goes from 0 to 14. 7's right in the middle. Being a logarithmic scale, a pH change of 1 unit is a 10-fold change in concentration, right? So if we're going from pH 7, perfectly neutral, to 6, 6 is just a little bit lower than 7, but it's 10 times more acidic, right? We go down to 5, it's just a little bit lower than 7, but it's 100 times more acidic. It's 10 times 10, right? So there's a biological tolerance that we have to take into account, and we'll have more to say about that as we go. Toxicity and inhibition, these are sometimes used interchangeably. True toxicity is a case where metabolic function doesn't return even when the material dissipates. And I think Mike was saying earlier about that problem that we had with the tetramethyl ammonium hydroxide and the poisoning of the slugs that occurred there. We never could regrow from that, and we had to reseed. So that would be a case of toxicity that was a long time in resolving. It's very unusual to see that type of thing. More often than not, what we are dealing with are inhibition, where once the metabolic interference or material dissipates, we're back going again. But what's important is, how do you figure out that something is going upside down? How do we identify and quantify it? So let's count. Let's kind of scratch this out. The aeration basin dissolved oxygen. If I have something that is impairing metabolic function, what would you expect your aeration basin DO to tell you from its normal? Zach is saying it's going up. You're exactly right, yeah. So take home for the day, dead bugs don't breathe, okay, right? So if they're not breathing or utilizing oxygen, we're going to be watching that DO residual. Now, is there a benign reason why the DO might just climb high? A benign meaning it's a no significance. Sure, diurnal flow. I don't have much. There's not much fuel to be burned, right? So the oxygen level, the residual, is what's left over after the fuel gets burned. So exactly right. We might have a very dilute flow. You know, maybe there was a gully washer or a persistent rainfall, and I've just got very dilute BOD coming into the plant. Sometimes, the first gully washer after a long dry spell, we might get a surge of BOD as it scours the sewers. Then we go from feast to famine then, right? So we watch that DO profile, and it may or may not be indicative, but certainly if the DOs are high, there ought to be at least a second question, right? So what story can I tell about that would make it okay to not do anything? It's kind of how I look at it. And if I see the high DO, then I'm going to look back and say, okay, what were my flows? What kind of loads can I account for a benign reason for that DO to be high? If I can't find one, then I better go to a second level and say, is there something really impairing the biology? So there's a test that we call a specific oxygen uptake rate. Here we're going to go out and we're going to grab a sample of the mixed liquor out of the aeration basin, and we're going to measure the rate of oxygen uptake. We'll just ask the bugs, hey guys, how are you doing? Are you breathing? Right? And it's a 10-minute lab test. We'll determine if we have run oxygen uptake rates kind of every so often, and we kind of know what's normal. And that's the key here, is that you have some baseline for knowing normal, then do an oxygen uptake rate. And what would you expect the oxygen uptake rate to do if there is impairment? So the DO residuals were up. The oxygen uptake rate it'd probably be low. Yeah, it'd probably be low. So look for something that's lower than your typical baseline. Something that you can also do is so I measure it and the uptake rates are low. It's like, hey guys, if I gave you something good, would you eat it? So do that. We can get some primary effluent, or we can get some GGA off the shelf, glucose glucamic acid. In other words, put a substrate, a known good substrate, and see if we get a normal uptake and activity, right? Check your biology, see if it's responsive. Simple thing to do. The microscopic exam, can we tell anything from the microscope? This is kind of a maybe. I don't know how many calls over the years I've gotten where it's, hey, Paul, everything's dead. It's dead. The biology is dead. Really? Wow. How do you know? Nothing is moving. It's dead. Now, they're not, again, climbing Mount Stephen, but they're interpreting then the motility and the normal higher life forms, the bugs that are normally there greeting and waving, that decided not to. They may be curled up, there may be signs of some real stress, but that part of the micro exam is not the part that's removing the carbon, the nitrogen, and the phosphorus. That's all happening at the flock level, and it's impossible with the kind of microscopy that we're doing here to tell a live bug from a dead bug, an impaired bug from a non-impaired bug. Now, we may, from time to time, I'll see, I can see that flock has deflocculated dispersion. Things kind of it looks like things have blown up. In fact, I think I've actually said that to people at times. You know, it's been nuked or it's been toasted or it's whatever. So I mean, there are some kind of gross physical indications that something's been very disruptive. But you cannot use the microscope to determine live from dead at the bacterial level. You can certainly assess that there's been some stressors maybe on the system that are affecting that higher life form. So I would say just always look for the opportunity to see a little bit more, but don't overread that. Bacterial counts, meaning counting actually quantifying or enumerating the live cells. Very few people are doing this on site, but these are services that can be done by outside labs. If you want to determine your active and viable fractions and total cell counts, these are specialized services that may be warranted if you really think there's an impairment that is in that underlying biomass. ATP measurements are, not too many people are doing them, but they're simple to do. OUR measurements are easy to do. And so the ATP and OUR are tests that I personally utilize. Again, we need historical data to kind of know where the normal values are, but if you've got that, then I would say those would be used. And then there's specialized advanced testing. TRA has utilized Dr. Lang, who's formerly at Auburn, for a lot of this. And there are analytical services then that can do inhibition testing and specialized. But again, that's farming some things out. But at the first level, we ought to certainly be looking at our DOs and our uptakes and make sure that it fits with what we know is happening. This is just illustrating this kind of report that came back from Lang that pointed out where we found the tetramethyl ammonium hydroxide. So it's really just saying, affirming what we've already talked about. Quats are compounds that are designed to kill bacteria. It's been interesting since COVID came on the scene over the last few years, how we've seen a little bit more quat impairment. Almost all of the wipes, the Clorox wipes and pick your brand, Lysol, or all of those, the active ingredient in those are quaternary ammonium compounds. And they're very good biocides. They reduce surface tension on the bacterial cell. It affects the membrane, and the cells lose permeability and basically lyse. They are good at denaturing proteins, and of course the enzymes that are the functional tools that bacteria make are proteins. So the quats are protein denaturing chemicals, and that affects the metabolic reactions, and stuff leaks out, and the causes death. So the quat impact is well known. Quats are widely used in food processing. It's a sanitation chemical for dairies and food processors and meat packers and any facility like that would be utilizing quats. They can it can be a problem. But unless you've got a fairly significant exposure to those, you're probably not going to see that. This is just an example then of a particular quaff that we looked at in the lab. And this is actually, I showed you this earlier in the day, so I won't beat this one any farther into your head. But this was the uncoupling, remember, where the oxygen uptake went up and the ATP went down. It was an uncoupled reaction. So that is the effect of that. So probably the biggest things that we've found in plants to improve growth pressure-wise ends up being related to improving the BOD-COD loading, and this is including the side streams. So we'll come back and be dealing with side streams tomorrow and the following day, because this is really significant in the whole picture of controlling the disposition of the nitrogen and phosphorus that we're trying to remove. And then the mystery compounds, these ghosts that come through in the middle of the night that cause inhibition, those are probably the most difficult, because you can't see them coming, and it's very hard to prove that what you have there. This is where we want to show our appreciation for those who work the collection system side of things, work out away from outside the fence line of the treatment plant, trying to keep a mindful eye on all of the contributors that do present some risks to us. So when we see the effluent meet its permit for TSF, BOD, nitrogen, and phosphorus, then this fishbone chart is really just trying to make the point that all of those growth pressures are working synergistically to accomplish that. We define then success by saying there are physical properties that we need to achieve and some biological properties. By physical properties, we mean that you're growing a mixed selector that flocculates, settles, and compacts, right? When it flocculates, settles, and compacts, that's the TSS, the effluent TSS compliance point, okay? Those properties. We measure that with settling rate and SVI, okay? So I've got to check the box on TSS, that's the physical part of it. Then I have to check the box on the biological properties, which removes the BOD, the carbon, the nitrogen, and the phosphorus, and produces an effluent that's non-toxic. That's all biological conversion. That's the biological competence that we spend a lot of the day trying to get full understanding of. And how do we control that? We control it by maintaining our dissolved oxygen. You may be using ORP control to monitor and manage the anaerobic part of a selector. You may or may not use ORP, but that is the control point. The tail that wags the dog as you're wasting, that controls the SRT. Okay. That manages the mixed liquor concentration and the growth rate. So you keep the right amount of sludge under the right oxygen condition. Then we keep the sludge in the right place, so we've got mass balance consideration, and we control the mass balance. That means that if we think of the activated sludge plant as a teeter-totter, on the one side of the teeter-totter I have solids that are aeration. On the other side of the teeter-totter I have solids that are in the secondary clarifier bed. The solids are always balanced in that plant, or shifting I should say, in the direction of the secondary clarifier, because you know what flows downhill and it's coming your way, right? The hydraulic profile says solids are shifting to the clarifier and the teeter-totter can't get out of balance, so we bring it back. And so what is the control vessel that balances the solids to keep them in the right spot? RAS, exactly. RAS is your solids balancing tool. WAS is your inventory control tool. That determines how much is on the teeter-totter, is the WAS, the wasting rate. The balance is controlled with the RAS, exactly. Then we're mindful of the pH and the alkalinity, so we keep the pH where it will allow that metabolic function to occur. And we're knowledgeable about inhibitors, toxics, and side stream. So that's how we succeed, that's how we control it. And then you put that into some sort of targets, right? You simply then have, and I'm not stipulating these for you, I'm just saying, just make this a simple then target-based strategy where your nutrients are controlled, your DOs are controlled, your cruise is controlled at different set points. You've got SRT control. You're controlling to an aerobic SRT of more than 9 days, or at least the other. You got a waste flow that's establishing a mixed liquor concentration. You got RAS flow that's paced with the influent flow. Isn't that a nice thing? Because that is actually now maintaining the balance, right? So it's self-pacing, monitoring blanket depth, alkalinity, keeping pH up there, and you've done a nice job on source control. So that's a long and busy day. This is a micrograph that's I sped up because it took about 5 minutes for this protozoan to meet its demise. And I wasn't trying to be gruesome about this, but it's kind of like I think brains feel at the end of the day like this, where at some point your head wants to explode, or you're kind of done, right? So yeah, when cells have had enough, they go that way. We'll stop the punishment of that guy. We're going to call it good for the day.